All right, good afternoon. So today we are looking at a couple of different things, but our goal is to help you guys get some skills and some practice evaluating written materials to determine their validity, their truth, and reliability, right? So we want to make sure that the sources that you guys read things from, you know whether they're to be trusted or not. We're going to go ahead and start off with this video here.
A few people have tried it. Nobody has ever managed to get anywhere close to what we got like today.
You have to believe you can do these things. It's not like impossible.
There's been a few people that have been like sort of following us.
Me, my boots and we're gonna make it.
I definitely think it's going to be the next big thing. Yeah, liquid mountaineering is actually Ulf's brainchild.
It's a new sport. It was not existing before.
You have to run very fast underwater.
I mean, obviously the first step was the most important one. When we discovered, oh my God, Jesus, we're going one step, we're going two steps, we're going three steps. We're discovering it as we go along.
While we're still on land, we try to get up really speed. Soon we touch the water. We try to get like a swimming machine.
It's not straight into the water,
In a curve, in a slight curve.
And by that bend, you're actually not allowing yourself to sink into the water, and you want to keep that skimming sensation going as long as you can.
Bonjour.
What gets us those extra steps are these shoes. The original equipment where it first all started was the equipment that would help repel water. We found some shoes by mistake, actually. Totally water repellent. It's like water off a duck's back. It takes actually a lot of practice, a lot of focus. I think if you don't actually believe that you're going to walk on that water, it's not going to happen for you. We've been working on a jet ski system, obviously that pulls us into the water with a bit more speed.
Be with yourself, believe in it. It's not about the miracle, it's just go for it.
Try to do it. If you fall down, try again.
People want you to think in a certain way, and this sport actually allows you to push your horizons further. It's not boxing you in and saying that's what you are. You're moving past it all.
All right, so go ahead and pause here. You probably have some thoughts about it. So go ahead and talk to your group members about this video and what your thoughts are on it.
A few people have tried it.
All right, if you haven't yet, pause here so that you guys can talk to your group. All right. The next thing that we're going to be looking at are these two videos, which deal with skydiving without a parachute. And again, what we want you guys to be thinking about, right, is what is the video showing me? What is it telling me? What do I believe and what do I not believe? And what are some of the reasons why? So before playing those videos, which we'll do in just a second, I just wanted to kind of remind you guys that your day 7 assignment has you kind of explaining some of these things on your day 7 assignment. it'll look like this, right? So thinking about the two videos that we're about to watch, which one is true? And then with your group coming up with lists of all the things that make one video more believable than the other, right? So you could be typing in here like things that make this video believable or not believable. And then same thing for the second video, typing in all the things that you think make it more or less believable. But again, you'll be kind of talking through that with your group as well. All right, we're going to go ahead and play this first one.
This is one of the wildest stunts I've ever seen. We've got a guy who's going to jump out of an airplane without a parachute, fall through a 3x5 opening in the top of a roof, and land onto a trampoline. It's crazy, but we're going to do it. There's two things that make this stunt possible. One is the special reinforced trampolines that will absorb the final impact from Travis's jump. The second is the geomagnetic positioning system that Travis is going to wear on his belt.
This device is revolutionary. It uses the magnetism of the Earth.
So the natural magnet of the Earth and the magnet that we're attaching to Travis have a natural reaction to each other. We, in turn, have an anti-dipole reaction, which as Travis descends towards the Earth, we'll be able to steer Travis through the skylight exactly down onto the trampoline.
And say, eye on the target, eye on the target, eye on the target, eye on the target, eye on the target. This is by far the most dangerous stunt that I've ever been a part of. Our margin for error is, well, we don't have a margin for error. If Travis makes a mistake on this, it's catastrophic.
Clear for departure, wind out of the southeast, 22 miles an hour.
Jump out of an airplane with no parachute.
Go to cam 1.
Sarah's deployed, Sarah's deployed.
Sarah's
open. GMPS is engaged. Come on, Travis, little right, little right. Can I get a wind check, please? Wind check.
a couple degrees off. The wind is too strong.
Little right, little right, little right. There we go, there we go. It's 4,000 feet.
I see the target. I'm right above it.
1,000 feet.
I got it.
300. Travis is clear. He cleared the opening. Post cam 4. Is Travis moving? Is he okay?
All right, so that was the first video. And then the second video we're watching is this one. Again, you can pause it at any point. You might want both of them in order to compare, or you might want to pause it here so that you can look at the things from that first video.
Did you know, on July 30th, 2016, skydiver Luke Aikens made history when he jumped from 25,000 feet out of an airplane without a parachute into a net on the ground, which set a new world record.
All right, we're just less than 3 weeks out, getting ready for Heaven Sent. We're in the final push of the training. There's a lot of focus from the film crews and the production guys on all the fitness and stuff like that, which is great, makes me feel better. But none of that stuff is what's going to keep me alive on the day. What's going to keep me alive is the jumping, this repetitive practice, practice, practice. If I miss this target, it doesn't matter how good a shape you're in or any of this other stuff that happens. So hitting the target is the most important thing. Accuracy, accuracy, accuracy. Fighting the wind, countering the wind, all that stuff. The next thing is that rollover. I need to roll over about 200 feet. I'm going to be going about 120 miles an hour, and roughly 1 second before I impact, I want to flip to my back and land real nice. It's different than a stunt roll. I have to fly my body around.
Now, apparently, this was a big story at the time. It was even aired live on TV with the name of the show called Heaven Sent. But personally, I've never heard of it before. I just happened to come across his YouTube channel with videos of the jump. But before I show you the jump, let's quickly talk about who Luke Aikens is and how he prepared for the jump. Luke, who was 42 at the time of the jump, is a third-generation skydiver who has been skydiving since the age of 16 and has deployed a parachute more than 18,000 times over the course of his skydiving and base jumping career. Luke Aikens is also a safety and training advisor for the United States Parachute Association, where he provides advanced skydiving training to elite military special forces. So I think it's safe to say he is more than qualified to know the risks associated with such a jump. Luke spent 2 years preparing for this jump, 1.5 years of planning, and 6 months of straight training. And Luke told me they never once jumped from a plane into the net until the day they did this one and only jump. Now, just to be clear, when Luke jumped from the plane, all he had was a GPS, a communication device, and an oxygen tank. What he didn't have was a parachute, a wingsuit, or anything else that might help him stop or slow his descent. After jumping out of the Cessna airplane at 25,000 feet, Luke quickly reached a terminal velocity of 120 miles per hour. Because Luke jumped from 25,000 feet, he had to wear an oxygen mask for the first 10,000 feet of the descent. After reaching about 15,000 feet, he passed off the mask and tank to a member of his support team who was skydiving next to him. Using his GPS and only the air currents around him, he lined up his fall to the center of a specialized 100 by 100 foot net, which was designed to stop Luke's fall as softly as if you were standing on a trampoline and merely dropped onto your back. The net, dubbed the flight trap, was suspended between the tops of 4 200-foot cranes. The netting itself is constructed from Spectra, which is a high-density polyethylene cord that is twice as strong as steel. When Luke reached about 200 feet above the net, or a little more than a second away from impact, he flipped onto his back and tucked his chin. Once Luke hit the net, 4 compressed air cylinders, which are connected to the netting via ropes and pulleys, slowed him down in the same way that you might catch an egg in your hand, by decelerating it gently over a distance. The total time from jumping from the plane to hitting the net took about 2 minutes. But when you were falling from 25,000 feet into a small net you can't even see from 25,000 feet, I bet it felt like a lifetime. Luke Aikens set a new world record performing this jump, and I bet you that's one world record that won't be beaten anytime soon. Anyway, that's the end of this video. Thanks for watching, and we'll see you next time.
All right, again, you probably have thoughts about both of those videos. Again, think about which one is true, think about some of the reasons why, and make sure that you guys fill that out on the day 7 assignment. Definitely talk through it with your group. They can help come up with ideas that you might have missed. All right. Again, pause the video if you haven't finished that. Make sure that you guys finish that up before moving on. Next thing we're going to work on is our main topic for today, which is whether or not cell phones cause cancer. So first, we're starting off with the table, things that you already know, things that you want to know, and things that you learned throughout the activity. So you should be able to fill out those first 2 columns, things that you know, or at least think that you know. and things that you want to know. What are you curious about? As we go through the rest of the videos or slides today, you guys will be able to fill in what you learned, again, as we kind of go through things. So again, pause the video here so that you guys can fill out that table. All right, you should have at least those first two columns filled out. We're gonna look at the EM spectrum, the electromagnetic spectrum, and kind of get a little bit more of an understanding about what it is, and how it relates to cell phones and how it relates to cancer and things like that. So this should help us fill out some of the I learned column.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
All right, so this should give you a little bit more knowledge about the EM spectrum. You're probably familiar with some of the things that were discussed in the video. Hopefully you were able to learn a few things as well. Don't forget to fill out the what I learned, as you're going through these, as you learn things. And again, pause the video, rewind the video at any time if you missed something. All right, well, how does this relate to sort of our overall project or overall plan? Well, we needed to know how cell phones communicate with the cell towers. And again, the cell tower communicating back with the other cell phone. And we realized that this was all because of EM waves, right? They're sending these radio or microwave signals to these cell towers. And so we need to know a little bit more information about those EM waves. And as we learned, right, there's lots of different parts of the EM spectrum that could be used for this. Some of those are not as useful, and I think you guys could come up with some ideas as to why we don't use visible light, right? Why is our phone not shining visible light to the cell tower? Well, it gets blocked by a wall, right? It would get blocked by your head or your pocket. So we want to make sure that we're using waves that are able to travel through certain materials so that they can actually get the signal to the tower and back to your phone. But why use EM waves in the first place, right? There's lots of other waves that we've talked about that they could use. Sound waves are an example, right? Would you want your cell phone like yelling your conversation to the cell tower and then having the cell tower yell your conversation back to your phone? Probably not. So there's lots of different reasons why we use the things that we use. We're going to kind of take a look at one of the main reasons as to why we use the EM spectrum, and that's because of the speed of light.
It's the week after Easter, and that means homes all across America are overflowing with stale Peeps. Now, you could either eat those Peeps, or you could use them to find the speed of light.
Finding speed of light with Peeps.
The speed of light is one of those numbers that people have chased for centuries. Galileo wanted to know how fast light moves.
Buonasera.
So he proposed an experiment.
Facciamolo.
He would uncover a lantern, and when the light reached his assistant, the assistant would quickly uncover his own lantern. Using a water clock, Galileo would keep track of the time between uncovering his light and seeing his assistant's light. Up close, there was no noticeable delay except for the split second it took his assistant to react. Then they started moving away from each other. Galileo figured the delay would get longer and longer because the light would need more time to travel the greater distance. But even when they were a mile apart, there wasn't a noticeable pause.
Che rabbia.
He couldn't have guessed that light had made that trip in 100,000th of a second. Centuries later, in 1849, a French scientist, whose name I can't pronounce,
Armand Hippolyte Louis Fizeau,
came up with an even better way to measure the speed of light, which was pretty impressive considering that people weren't even using light bulbs yet. He took a toothed wheel and spun it faster and faster. He shot a beam of light between the teeth and reflected that beam of light off a mere 5 miles away. By the time the light got back, a tiny fraction of a second later, the teeth had moved over just enough to block the light. No light made it back through. But if he made the wheel spin a little faster, the teeth would move over one whole position and the light could get through. So when
Fizeau
saw the light, he knew the wheel was spinning so fast that a single tooth was moving over one place in the time it took light to travel 10 miles. With some quick math,
Armand Hippolyte Louis Fizeau
determined that the speed of light was 700 million miles per hour, which we now know was only 5% off the actual value. Today, I can find the speed of light in my kitchen, and that brings us back to Peeps.
Finding speed of light with Peeps.
And a microwave.
And a microwave.
And just a little bit of physics.
And physics. Just a little bit.
Microwaves travel at the speed of light. And like all waves, their speed is determined by how fast they go up and down, that's the frequency, and their wavelength. The frequency is written on the side of my microwave right here, 2,450 megahertz. So we've got the frequency. Now to calculate the speed, we just need to know the wavelength. And we can find the wavelength by microwaving Peeps. I'll set it on low so the Peeps don't just explode. And let it run for a minute or two. Inside, microwaves are bouncing around. In some spots, there isn't much energy at all, and the Peeps in those areas stay cold. In other spots, there's lots of energy, and the Peeps get really hot. Those hot spots are half a wavelength apart. So in theory, if I measure the distance between melted Peeps, I can find the wavelength. And sure enough, some of the Peeps are really gooey, while others haven't melted at all. Poking around, I found a rough location for a handful of hot spots, and I measured the distance between them. Those average out to 2.43 inches, so that's half a wavelength. Multiply by 2, and we get a wavelength of 4.86 inches. So now, to find the speed of the microwaves, which, remember, is the speed of light, I just have to do the math. Frequency times wavelength, 2,450 megahertz times 4.86 inches, gives us about 12 billion inches per second, or 676 million miles per hour. And that's pretty close to the actual speed of light.
We just found speed of light with Peeps.
Wow, that's a lot of hot chicks. I was trying.
All right, so we've got that. Obviously, speed of light, very, very fast. And so it makes it so that there's basically no noticeable delay when sending a signal all the way to the cell tower, and then that cell tower sending the signal all the way back to the other phone. We've talked about lots of the other useful reasons why we use EM instead of something like sound and whatnot. So again, you should be able to kind of come up with some of the reasons as to why we use certain waves. All right. Again, as we're kind of going through things, we do need to talk about other waves. And so we are going to be looking at sound waves. And we want to be thinking about whether they are good or whether they can, in fact, cause harm. And so we'll go ahead and take a look at that. We could think to ourselves, well, for the most part, sound waves are totally fine. I'm talking to you right now. You guys talk to each other all the time. You listen to music, right? For the most part, that's probably not a big deal. Although you probably have heard that, you know, your parents yell at you about listening to your music too loud. Oh, you're going to hurt your ears or whatnot. So there is potentially something going on with sound that could cause some damage. And we might need to think about, okay, what would cause that? What does it depend on whether or not the sound wave is going to be harmful to you? Apologies for that. Did not know that that was going to kick in automatically. But yeah, so there are two kind of key things that play a role, right? One is frequency, and different frequencies can be harmful. If it's high enough frequencies, that can cause some issues. But the big one is the amplitude. And amplitude for sound is just how loud it is. Whereas frequency is about the like pitch or tone of a sound. So you have your like low frequencies, your low sound waves, and those ones are going to be lower pitch. And then you've got your higher frequencies, and those frequencies are higher pitch and therefore higher frequency. Where again, as if we're changing the amplitude, right? A low amplitude is a quieter sound, and then a big amplitude sound is a louder sound, more volume. This is the frequency going up. So you could kind of see that low frequency getting higher as it goes. Now, light waves, we want to think about the same sort of thing, right? We want to think about, is this possibly damaging? What might cause it to be damaging? And again, we have light surrounding us constantly, right? And if it's all damaging, that would be a bad thing. So it must not all be damaging. And we want to think to ourselves, what could cause it to be damaging? And think about what types of light do we know about, or what parts of the electromagnetic spectrum are parts that we've heard of being issues or being problematic. And again, I think some of you guys already know a couple of these light waves that are damaging or potentially damaging, and you protect yourself against these things. When you go out into the sun, if you're going to be out at the beach all day, you probably put on sunscreen to protect yourself from a certain part of the electromagnetic spectrum, namely ultraviolet. And you probably have had x-rays at the doctor's office before. And you'll notice that they will either put a nice lead vest on you if they're doing like teeth x-rays or something like that. And they'll stand in a different room, right? Or they'll stand behind a protected wall so that they can minimize your exposure for the parts that don't need to be x-rayed, and they minimize their own exposure by being outside of the room. And so we know at least a couple of these that could be damaging or harmful. So let's take a look at the kind of the whole spectrum here. We've got sort of all of these different frequencies. It's all light, right? It's all electromagnetic radiation, but different frequencies behave differently. And so here, sort of at the lower end of things, we've got like radio waves. This is what your old TVs used to use. This is what your radio used to use. We get a little bit higher energy, a little bit higher frequency, and we get into microwaves, cell phones and ovens, kind of in that territory. We get into infrared. So infrared is like heat, right? Like a conventional, normal type of oven would be there, toaster, right, would be here, heating lamp would be here. We get into ultraviolet, right? This is the type of sunlight that is damaging and causes you to tan. So we use it in tanning booths. But again, you're exposing yourself to lots of this ultraviolet radiation. If we go even higher, we get into the X-rays here. And in between these, we kind of missed off gamma, but we'll talk about that in a second. In between ultraviolet and infrared, this is where the visible spectrum is. It's a very, very small part of the spectrum. We'll see it better on the next picture. But what we see is a very, very tiny window into this whole electromagnetic spectrum. And then X-rays, of course, are used in medicine all the time. If we go even higher energy, higher frequency, we get into things like gamma ray, which you guys have probably heard of mostly just from superhero movies and cartoons. We've got a nice little sort of picture on the side here that kind of shows these, right? Radio waves, microwaves, infrared. You can see as we go, the wavelength is getting shorter, right? Shorter and shorter wavelength, higher and higher frequency as we go to the right, with visible kind of stuck there in the middle. Again, another picture just to kind of see things, really kind of able to see a little bit easier, sort of that infrared, how infrared bleeds into the red part of the spectrum, the visible spectrum. And then, of course, blue goes into sort of that violet, into the ultraviolet part of the spectrum. And, of course, we can just see that tiny little gap in the middle there. Well, we want to think about whether or not these things are helpful or harmful. And obviously they can be both, right? So we need light to visible light to see, and we obviously use it for a lot of our technology. And so it is both, but we want to specifically kind of narrow in on when it can be damaging and when it can be helpful. So X-rays are a great example. We know that X-rays are very, very useful, mostly for taking pictures of the bones in your body. But because X-rays damage cells, they can cause cancer, which is why we try to reduce the amount of exposure to X-rays, if at all possible. But scientists have also started to use them to treat cancer. So yes, it could cause cancer, but it can also be used to treat cancer. And the way that it's used to treat cancer is, again, it can damage cells. And so if you specifically target the cancer cells and damage the cancer cells, right, you can kill off those bad cells, hopefully just targeting the ones that you're trying to and not targeting other cells. So again, we've kind of got this picture of this sort of crosses and everything. And there's a lot of what's called constructive interference. All the waves are kind of adding up at the center point. And that allows it to be more impactful at just one location rather than all the way along the path. And so they all kind of affect things everywhere, but really focusing in on that center part where you're trying to damage those cells that you want to damage. So we're talking a lot about things causing cancer, and there's actually a word for this, and it's called carcinogen. A carcinogen is something that has been linked to causing cancer. Does it mean it's going to cause cancer every single time? No. What it means is that it increases your likelihood of developing cancer. Some other known carcinogens: tobacco smoke, asbestos, and we talked earlier about UV light. Here's a quick video kind of talking about some of these things.
Tumor position that changes due to respiration presents significant challenges in radiation therapy because reducing toxicity and improving results hinges on the ability to precisely focus dose and deliver steep gradients. The CyberKnife M6 system with Synchrony respiratory tracking is the only clinically proven robotic SBRT SRS system to combine conformal beam shaping and real-time respiratory tracking. CyberKnife M6 with Synchrony resolves inherent limitations in conventional linear accelerator designs while providing an expanded range of radiotherapy applications. It is simply the best solution for tracking and treating moving targets. The treatment process begins with image studies used to create prescribed plans and generate DRRs to facilitate treatment planning, including a planning process that accounts for the CyberKnife system's continuous image guidance. Upon authorization of the treatment plan, Reference DRRs are generated to be registered with live images of the patient at the CyberKnife's treatment console. Here, tracking and other treatment-related parameters are refined. During treatment, optical beams monitor external markers attached to the surface of the patient. Taking reference images throughout the respiratory cycle allows the system to continuously monitor the patient's breathing pattern, even accounting for respiratory anomalies in real time. The CyberKnife M6 system is unique in its ability to track, detect, and correct for patient and tumor movement with industry-leading accuracy. The Incise multi-leaf collimator adds active beam shaping to the system's tumor tracking, enabling physicians to treat larger tumors with precise dose distribution, sparing critical organs and healthy tissue. Delivering radiation in a nearly limitless 3D workspace, the CyberKnife system paints the tumor from numerous angles with non-coplanar, non-isocentric beams. Such clinical precision means physicians can confidently prescribe hypofractionated therapy that can result in reduced margins, reduced toxicity, quicker recovery, and better patient outcomes. The CyberKnife M6 system with Synchrony respiratory tracking, the best solution for treating and tracking moving targets accurately.
So we just wanted to kind of show this. I know that there's a lot of techno babble going on there, either medical babble or techno babble. But again, just showing you that we can, in fact, use these things and the things that you're learning in class to, develop strategies for helping people, right? And obviously, if we need to treat a tumor, we kind of saw ways that we could do that with electromagnetic radiation, but humans, patients breathe, right? And so you need to adjust as you go. And so developing a system like this allows you to track that part that you're trying to target while things are moving around. Here's another one. Again, a lot of things in the health-related careers can come from these areas of physics.
Hi, my name's Christy Tonning, and I am the director of the OHSU Radiation Therapy Program. As the director of the Radiation Therapy Program, I am responsible for the education, both classroom and clinical, of radiation therapy students. Now, I didn't start out as the director of the program. I actually started out as a radiation therapist. So radiation therapy, I think, is one of the best professions and careers out there. In healthcare, we need a whole group of people working together towards the primary goal of patient care. So in radiation therapy, we have radiation therapists who are the front line for our patients. We have medical physicists who actually calibrate and check the physics and calculations on the machines. We have dosimetrists who are a little bit like engineers. They get images of a patient, and in that image, the doctor says, here's the cancer that we want to treat. Here's areas we don't want to treat. How can we do this? And then in that group, we have physicians, and then we have nurses. And because we have so much technology, we have a bunch of IT people that help with the different computer systems and engineers that help with our machines. So all of those people are needed to treat one single patient that has cancer. So in class, you are learning about waves, and there are many types of waves. The waves that we use in radiation therapy are high energy X-rays or gamma waves. The goal of radiation therapy is to kill the cancer cells. Cancer cells are cells that have mutated. Often cancer is next to healthy tissue or within healthy tissue that we don't want to radiate. And we all have DNA. And what radiation does, if we're successful, is it'll damage the DNA so much, we call it a double strand break, so that the cancer cells can't repair. Now, healthy cells are healthy, so when they get some radiation, they can repair. We know exactly where we're giving it. We know exactly how it's working because of the team that has quality assured that it's doing what we say it's doing. So day after day of this, we'll see the healthy cells repairing and the cancer cells dying off. There's many different types of cancers, and all cancers don't react to the same dose of radiation or to the same number of treatments. We use something called evidence-based practice, or you could say evidence-based science. And based on the evidence, checking the side effects, checking the outcomes, that informs then what we continue to do. If you keep working and you keep learning and you reach out and explore different career options, different ideas, the world will open up to you. So keep working hard. Freshman physics, I can remember that, thinking, how is this going to be applicable? I never imagined that I would actually end up in a field that utilizes physics every day. But what helps me utilize that physics every day is the patient contact and the technology that enforces it. So again, it's that combination of patient care and technology that really comes from building up by taking your maths and your science and your communication classes, but can lead into all types of careers.
So again, even if you think that you might not ever use it, just having that knowledge is important because you might end up using it. So it brings us back to that question, right? Do they hurt? Well, kind of depends, right? Do all frequencies at all amplitudes hurt? No. And this is where we get into another key word here that she sort of glossed over in her explanation, but it's the word ionizing. And what we mean by ionizing is that certain light will be considered ionizing if it has enough energy to break apart molecules in your cells, including your DNA, right? And if we break that DNA, that's what could end up causing it to become cancerous. She was explaining that they try to break multiple parts of the DNA, and that way the cell can't repair itself and it dies off rather than becoming cancer. So this is key, right? Not all EM waves are going to have enough energy to break apart molecules in your cells. Only certain ones are. And so if we look at kind of where we find these ones that have enough energy, it's all this higher energy waves, right? It's all the stuff that's ultraviolet and above. And not all of ultraviolet, right? Just parts of ultraviolet, X-ray, gamma rays. Those are the ones that have enough energy to cause the actual DNA in your cells to break and therefore could end up becoming cancer. Now, we have this little spot in here, microwaves, that's also highlighted, and that's because it's not ionizing. Your microwave oven will not cause your cells to, become cancerous or anything like that. What microwaves do is they actually resonate with the water molecule. And what that means is that they cause the water molecules to vibrate very, very energetically, which causes the water to heat up. And of course, if the water's in something like your food, it's going to cause that to heat up as well. And so that's why we kind of highlighted that section as well, because I know there's always concerns about microwaves. Again, just kind of showing that on this graph as well. Again, it's that ultraviolet, X-ray, and gamma that are the actual parts that would be ionizing. UV can cause cancer, right? Ultraviolet is ionizing, but blue light, which is right next to that, doesn't. And so again, sometimes those frequencies are right next to each other where you run into perfectly safe and then not so safe. And so again, just kind of keeping in mind that it's all about the frequency, and the frequency is what determines how much energy it has, and therefore whether or not it's going to be ionizing. All right, your next thing is going to be reading assignment. And so on that day 7, right, if you continue, do cell phones cause cancer? So we've got two different readings. The first one, again, it'll tell you the source, some description about the source, some information about that. And again, it's going to kind of go through that stuff. It wants you to read it. And then after you've read it, we'll get to this part. Makes 4 claims. Highlight using colors below where these claims are in the reading. So again, look back at your reading and highlight as necessary about the claims that it is making. So we've got these things here. One is that ionizing radiation is high frequency and therefore high energy. We want that to be highlighted in orange. So try and find that in the reading, highlight in orange. The next claim is ionizing radiation, like X-rays, is known to increase the risk of cancer. Again, highlight in yellow. Non-ionizing radiation is low frequency and therefore low energy. Find that in the reading and highlight that in green. And the last one, non-ionizing radiation, like radio frequency radiation, causes heating to the body, but there are no clear effects on the body. That we're going to have you highlight in blue. So at this point, you should have your article here that should have 4 different colored highlighted areas. If you're curious about more information for the website that we got this from, you can, again, go to the link here to get to that website. You should also be able to have completed your What I Learned part of the table. Now that we've kind of gone through all those videos, all those slides, and this reading, should help you have that complete. And then the last thing to take a look at are these 2 sources here. We've got these 2 sources here, and we want you to click the link and then describe the resource. So this first one here, we'll click the link to go to Article A. We're going to describe the resource. What type of writing is it? Is it informative? Is it persuasive? Is it an advertisement? So on and so forth. Again, think about what you guys learned in English class about the different types of writing. Next one, how easy is it to determine the author? Who wrote this article? And how do you know who they are? Again, fill that out. What do you think the goal of the author was? Right? Why did they write this article? Because again, they might have different motives based on their purpose of writing. After reading the complete article, think about the confidence that you have in the article's authenticity. How truthful do you think the article was? And then anything that you found troubling about the article, right? If there was anything that brought up some questions or you're like, this seems a little bit fishy, right? Make sure to include that here. Last but not least, what sources are cited? Where did they get their information from? Are they just pulling it out of nowhere, or do they have some sources? And how easy is it to find those sources? And how reliable and credible are those sources? So that's what we want you guys doing. And then, of course, once you finish with that article, do the same sort of things for the second article, where you're looking at the purpose and all those different things. Make sure that you guys turn this in when you guys are done. There's a last article here that, again, it is sciencey looking, but take a look at it. Again, kind of look at some of the things that really make this article suspicious, right? So not doing all the things that you did here, right? Instead, open this article up and kind of think about what are 5 reasons why you shouldn't believe this article. Again, we're just trying to get you guys to be skeptical. All right, take a look at those. Turn it in when you are done.